We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
Greetings, junior scientists, and citizens of the great big weird wild wonderful world in which we live. As always, I'm your humble science communicator, the Great Orbax. Broadcasting you here live from Physics Hollywood, California, in the Department of Physics at the University of Guelph, in Guelph, not in California. We're back after somewhat of a hiatus, so welcome back to all of our viewers out there on the interwebs. Tonight, we have an opportunity to meet with two incredible experts to talk about images that I think literally have been the most talked about space images in the longest amount of time that I've ever can honestly kind of remember. And I'm old, so that's a while. Now, here we go. As you know, this is a live stream. You can tell that mostly because most of you are likely watching live now, and we are able to take your questions and ask our experts. So in the comment section, feel free to go ahead and ask any questions, or just feel free to say hi and let us know how you're doing. And we'll pull these questions up as we come through. But for those of us of you who have come to the physics live stream here at Guelph Physics in the past, you know that when we start these things, I pride myself on my hastily written 2 to 3 sentence monologues that I start these streams with. And so as a result, I've done one of those this afternoon. I guess we could call it this afternoon. 2 hours counts as this afternoon, 2 hours ago, right? So here we go. Here's our introductory monologue. Let's bring this up. I didn't have time to memorize it because it's so good. With its signature 6.5 meter wide honeycomb of golden mirrors, the James Webb Telescope is not only impressive as the most powerful space telescope ever built, but perhaps even more impressive is how it has captured people's imaginations across the globe. And why not? When it was launched on Christmas Day back a mere 7 months ago today, it was already a global symbol of unity, a project that united thousands of scientists, engineers, and technicians from 14 different countries together in 40 million hours of work to hurl a looking glass the weight of a school bus and the size of a tennis court 1 million miles into space and hope for the best. And frankly, the best is what we got. When the images came back 2 weeks ago on July 11th, the world was watching. And tonight, we get a chance to talk about what it means to our experts that we have assembled here. Our guests this evening are, well, 2 previous guests of our live stream. I'm very excited to welcome them back. We're going to start out. Based in Guelph, Kate Howells works to engage the Planetary Society's myriad audiences in the adventure of space exploration. As Canadian Space Policy Advisor, she guides the Planetary Society's positions on space policy and advocacy in Canada and connects Canadian Planetary Society members with opportunities to advocate for Canadian space science and exploration programs. She's also the author of Space as Cool as F***, exclamation mark, and also as a member of the board of directors of Royal City Science. Please put your virtual hands together and welcome to our live stream, the one, the only Kate Howells.
Hello, thank you for that wonderful introduction, Orbax.
No problem. Well, welcome back, Kate. Are you excited for this evening's stream to discuss the James Webb Space Telescope images?
I am, yes. It's always exciting for me as a person who loves space, works in the space field, thinks about it, talks about it all the time, when people in my social life who don't normally think and talk about space all the time get excited about something. And that has been the case with the JWST images. Everybody's jazzed up about them, and for good reason. They're extremely cool. I can't wait to dig into them.
Fantastic. Now, as is tradition here at the Guelph Physics live stream, I'm going to start with an opening question for you. And that question is this. If you were to tell somebody about the most exciting thing about your job, what would you tell them?
I think the most exciting thing about my job is that I get paid to learn about stuff that I find really interesting and then tell people why I think it's interesting. As like a nerdy person, that's sort of the dream. I just get to soak up all this information and then regurgitate it in a form that I think will resonate with people. I get to just be like enthusiastic about something that I like for a living, and that's great. Yeah.
Fantastic. I mean, that is kind of the dream, right? Is to find something you're excited about and something that you love, and then get to share it with other people.
Yeah, absolutely. I mean, and I think it's also very lucky that the thing I love is space, which is easy to get other people excited about. Like I always say, if I was like an educator and communicator and advocate for like soil science, which I think is really cool and really important, but it's not as like accessible, like the reason why it's so cool and important to like the average person. But you show a picture like the ones we're going to look at tonight of space and everybody's like, oh yeah, I get that, that's cool. So I feel like I have an easy job getting people interested in space.
Well, you heard it here first. Kate hates soil.
So no, I like soil. I want to make that very clear. Soil science but I think you're right. Cool.
I think there is an incredible unifying, just an emotional response to space that I think resonates at our core. And that video that we opened the stream with was narrated by Carl Sagan, the founder of your Planetary Society that you're a part of, who also shared that passion for just sharing space with the world. And I think more so, and I say this as a physicist who's studied condensed matter physics, which again is another thing to try to get people excited about by just showing them a picture. Doesn't always work. There's just something unifying about the idea of exploring out there, of going outward and of probing that I think just brings people together. Who among us hasn't sat down, looked up in the sky and thought, what's out there?
Yeah, absolutely. And it stretches back, as long as humans have been humans, we've looked up at the night sky and contemplated it. And I think it's, you can't say the same thing for every branch of science. And so, yeah, I think it's pretty unique in that way.
All right. Well, let's welcome our next guest this evening. Pulling up the bios. Our next guest this evening is Nathalie Ouellette, who's an astrophysicist, a science communicator, and a lifetime lover of all things space. She obtained her PhD in physics and astronomy at Queen's University in Kingston, Ontario in 2016. Her research focuses on galaxy formation and evolution, particularly those found in clusters. Nathalie is currently the coordinator of the Institute for Research on Exoplanets, you may have heard it called IREX, at the University of Montreal, and is also the outreach scientist for the James Webb Space Telescope in Canada. Collaborating with the Canadian Space Agency, she's a frequent contributor and analyst in Canadian media on everything related to space. She organizes and participates in science outreach events from local to international scales and encourages the interest and participation of youth and the general public in space science and to increase scientific literacy in Canada. Let's put our internet hands together for the one and the only Dr. Nathalie Ouellette.
Hello.
Hello. How are you this evening?
Good. I'm very good. I'm recovering from COVID, but other than that, I'm good.
Egads.
Yeah.
Well, I was kind of sad. I don't know where to go with that. I guess that's the thing these days. I mean, even coming after 2 years, as things start to open up again, I think a lot of our colleagues have kind of finally gotten it.
I think I got it when James Webb released its first images because I met so many great people. But there's a lot of viruses out there to meet as well, unfortunately. So I think that's what happened.
It's true. And of course, we for those of us watching the NASA live stream, we saw you for a brief moment appear momentarily from was that from IREX?
From the Canadian Space Agency.
And then the feed fell out.
Yeah, that's right. Unfortunately, there was a technical difficulty. But we still recorded our presentation of the Canadian first image, which is actually a spectrum. So it's available on the CSA's Twitter, Facebook, all the social media. So do check it out. Myself and my colleague, Sarah Gallagher, we introduce it. I think we do a pretty good job. Unfortunately, it didn't make it to the NASA feed, but still.
You did a fantastic job. You made all Canadians everywhere proud. It was it's great to follow up with that. And what we'll do is we'll link it in the description, the YouTube description after this, so people can tune back in and get a chance to look at it. I'll ask you, Nathalie, the same question that I asked Kate. What's the most exciting thing about your job?
This is always the issue with going second. The first person has the potential to steal your answer, or not steal, but have a very similar answer. So I still do a little bit of research, but a lot of what I do is related to outreach, project management. And so the two things that I really love in life is to learn and to teach. And I love the fact that I get to interact day to day with researchers who are at the cutting edge of research, doing all kinds of science. As the outreach scientist for the Webb Telescope, I get to talk to people who do exoplanets, but also galaxies and solar system objects and stars. I love all things in space. So I get to learn all these things from the people who are doing that research, but then I get to teach about it as well to the public. So I really love those two aspects of my job.
That's fantastic. That's great stuff. So I guess, we're going to there's a lot to cover tonight. We're going to get into the images. I want to talk a little bit about the actual space telescope itself and the mechanics of how it works. But I think I want to start a little bit by for those of the viewers who haven't had a chance to actually see you in previous streams, either of you, I want to ask a little bit about your journeys to where you are now. And how you came about being contributors to the space field and as science communicators in general. I guess maybe Kate, we could start with you. Oh, actually, you know what? You went first and you stole most of Nathalie's response. So I think it's only fair, I guess, to start with Nathalie in case you both have the exact same origin story. She gets a chance to tell it first at the very least. Nathalie, can you give our viewers a quick sort of rundown of how you came to be this expert?
Absolutely. And I don't think Kate's going to have the same story as me. So she's probably safe there. So I've known that I wanted to be a scientist from a very, very early age. Both my parents are engineers, so I grew up with a lot of science at home. So I went and did a bachelor's in physics at McGill University. But I knew that space was really for me. So as soon as I could, I did research projects in the summer, even during the semester for credit, with astronomers there. And I found a really great program at Queen's University in Kingston, where I did my master's and my PhD, working on galaxy evolution with Professor Stéphane Courteau, another Quebecois person. So we had that in common. We spoke French and English. But I also fell in love with outreach while I was doing my PhD. I was the coordinator of the on-campus observatory. So I ran the entire outreach program for 6 years while I was there. I loved it. I loved getting to talk to kids and the general public on top of doing my research. So when I wrapped up my PhD, I figured, okay, can I make this a career, science communication? It's sort of burgeoning as a field. So I tried it. It's not super easy because there aren't that many jobs in it. But the McDonald Institute, which is a new institute, relatively new, on astroparticle physics, just opened up at Queen's. I became their first communications education and outreach officer. I was there for a year and I built their entire outreach program for that first year. But I wanted to come back to Montreal. I wanted to come back to pure space. So the position that I have now opened up, and I've been here for about 4 years now.
That's really interesting. We've talked a lot on this stream before about this idea of science communication and how previous to sort of in the last maybe you could say 5 years, maybe 5 to 10 years, it kind of just became its own entity and became its own thing as social media platforms kind of exploded. There became this room out there in the world to have more science communicators than when I grew up. You would see 1, 2, maybe 3 people that you could say, oh, that's someone who's on TV who had a science show. Now, as things have expanded, people who have those capabilities and make it easy for other people to understand science have all these other avenues to come into. But it's interesting how, for my personal journey, that was something I always wanted to do as well, but it never really became a thing until like 2010 or so.
Yeah, I absolutely agree. And I think social media gave researchers who already had an interest in outreach a platform to do it. A lot of people wanted to do it, didn't actually know where to go, where to do it, who to connect with. that allowed that. But I think another really big piece of the puzzle is that research institutes are seeing the great value in having paid
100%.
positions that are doing outreach. They can be people with scientific backgrounds or communication backgrounds, but they do outreach full time, paid. So all the work of the researchers doing out there, volunteer, that's fantastic, and I praise them for it. But it's really important to have paid positions as well in the field.
100%. So Nathalie's coming down on the controversial side that the internet was a good thing. So that's
For some
great to hear.
things. For some things.
Well, I guess we'll ask Kate, how did you come upon your position?
Yeah, so the only copycat answer I've got this time is that I also did my undergrad at McGill University in Montreal. And I was doing that in psychology in the arts stream. So McGill, you can do psychology in the sciences or in the arts. I started in the arts thinking I wanted to be a teacher or something. I really wasn't interested in science that much. And I certainly didn't know that I was interested in space until about halfway through my undergrad. McGill offers really great science courses for non-science students, including in their Earth and Planetary Sciences department. And I started taking those courses and I started reading the works of Carl Sagan. And I just became very fascinated, kind of obsessed with space. But I was in an arts degree. It was kind of too late for me to transfer into the sciences. So I looked to ways that I could pursue my interest in science and in space, particularly without having to do the science and engineering track. And I wound up going to a master's program in science policy at the George Washington University in Washington, D.C., which I wound up actually really not liking at all. I realized that science policy, as much as it's kind of an interesting way to apply an arts background to a science interest, working in that kind of government framework was really just not my cup of tea. But while I was there, I learned that I was very interested in science outreach and public communication. That's what I wound up writing most of my papers about, is on sort of how engaging the public is critical to having strong space programs. And I had done some science outreach stuff as an undergrad as well on sort of like brain. I was studying like cognitive science, like brain processing stuff. So I did outreach on that. So I kind of started to realize, oh, maybe I'm interested in this outreach kind of thing. The initial interest in being a teacher kind of tied in. So I was kind of piecing together these different parts of myself and my interests that hadn't really been apparent before, and realized that I wanted to do outreach around space stuff. And I was extremely lucky in that the grad program I was at in Washington was affiliated with the Planetary Society. One of our directors is a professor at George Washington University's Space Policy Institute. So I got connected with them. I expressed my interest in doing the kind of work they did. They expressed an interest in expanding their work into Canada because they're a US-based organization. And I volunteered to help them navigate the Canadian space policy landscape. And that was about 9 years ago now. So I started out with them working specifically on kind of figuring out how they could get a footing in Canada, and then wound up moving into the communications department. And now I oversee our social media strategy. I do a lot of writing and editing of articles and newsletters, and I help with video creation. I help with overall communication strategy, and especially with an eye to connecting with international audiences, especially in Canada. So I've kind of had this winding path. I'm one of the few people for whom dropping out of grad school made my career. So I know you might not want to hear this on a university stream, but
that's okay. I was the exact same way. I dropped out of my PhD 2 years in, and look at me today.
Yeah, some people, they say those who can't teach. Like sometimes it's true. Sometimes if you don't want to actually do the thing, you might want to teach about it. And that was what I found with science. I was never the type to want to do science research myself. I've always been like not detail oriented enough and not wanting to get so precise in my focus. And I have just really found my niche in doing outreach in science. I love it a lot.
It's interesting to me, this idea that a lot of our students, I think, get bogged down in the concept that, okay, I got to get my 4-year degree, and then maybe I'm going to continue in academia. I need to do a master's, then I need to finish my PhD, and then I'll start looking for jobs. When realistically, a lot of the people that I speak with have had such a circuitous journey to where they are today that I mean, I hate to say, oh, just follow where your interests lie, but you kind of should just be following where your interests lie and not be afraid to take that journey. And I think for a lot of people, the fear is taking that journey. And speaking of fearful journeys, we're 21 minutes in and we haven't even spoken of the fearful journey of the James Webb Space Telescope yet into space to observe what we're going to look at today. So unless there's anything anybody wants to add, I think we could get on to actually discussing the Webb.
For sure. Let's do it.
Let's do it. Yeah.
Great. And I'll point out again, we are live streaming. So if you're on Facebook watching us, or if you happen to be following Guelph Physics on YouTube and you have questions as they come up, put them in the comment section. We'll bring them up. Saksham, I want to ask you to bring up that ESA video because I want to start off by talking about the actual James Webb Space Telescope itself. I don't know about the two of you or any of our viewers. I got up at 6 a.m. Christmas morning, which I didn't even think of, but I'm shocked that it is 7 months ago today, and watched the actual launch with my wife and my cat. And it was pretty exciting to actually see the launch. Go ahead and you can play the video, Saksham, as we chat about it itself. Now it's a pretty impressive set up with the unfolding of the satellite as it takes off. I don't know who wants to maybe lead us through this, but I believe it took off in Papua New Guinea. Am I right?
In French Guiana. So
French Guiana, sorry.
Yeah, so the launch port is in Kourou, French Guiana, in South America. It's one of the contributions of the European Space Agency near the equator, like a lot of launch sites, using an Ariane 5 rocket, so very reliable rocket. And the launch went really fantastically. I was actually supposed to watch the launch from the Space Telescope Science Institute in Baltimore with all my colleagues, but Omicron made sure that wasn't the case. So yeah. I was definitely awake for this. I didn't really sleep much the night before, if I'm honest.
Well, to me, one of the most amazing things about this was that this telescope, which basically becomes the size of a tennis court, was folded up like origami and shoved into the nose cone of this Ariane 5 rocket. That's a fairly common thing, I think, but this is such a complex machine. Was there a lot of worries around whether this would unfold properly?
Stuffing the payload into the nose cone is a common thing, but for it to require over 300 mechanisms to unfold, that's less of a common thing. It's probably the most complex deployment that's ever been done in space. And that's one of the reasons why there were multiple delays in the launch, because we wanted to make sure that it worked. There was lots and lots of testing, folding it, unfolding it on Earth, making sure that it would survive vibrations and acoustics and the cosmic rays and micrometeoroids and all those kinds of things.
Yeah, we've had this discussion about launching pieces of equipment to Mars, because we have one of our professors here works on the Martian rovers and has sent equipment to Mars before. And it's always a thing you never really think about, well, I don't anyway, the amount of vibration that these things have to go through. But a specific thing about the Webb that was fascinating to me was how automated is the unfolding of all these segments, of all the actuators, of all the mechanisms that deploy this? Is this being done manually from ground control, or is this all built in as an automatic sort of unfolding that takes place over time?
So there is some automatic components to it, but there is a ground crew that is following every single step. There's a timeline. It's like this giant Excel sheet where like the fraction of the second is basically like timed out, like this happens next, this happens next. And we have confirmation that the correct thing happened for us to go on to the next step. So it's actually quite manually operated from the ground.
That's phenomenal. And I don't know if you happen to know this. This is again something we discussed with the idea of Mars, but what's the communication time between the Webb and Earth, since it's what, 1.5 million kilometers away?
Yeah, so it's only about 5 or 6 seconds of a delay. So it's really not that bad. The communications arrays underneath, it's communicating with NASA's Deep Space Network, the same network that communicates with a lot of probes. The Voyager probes still use that as well. So the delay is nothing like the challenges that you have for like a Mars rover situation where it's like several minutes of delay.
Saksham, can you bring up those last couple shots of the video? Yeah, perfect. So what are we seeing here? We're seeing this big, giant, sort of folded out shield. And this is a heat shield, am I right?
So yeah, it's the sun shield. I don't want to be hogging this, Kate. If you want to like jump in and do any of these bits.
Well, I feel like you know the technical details better than I do, so I'll let you keep going. You're doing
All
great.
right.
And Kate, it does look very much like the Planetary Society's light sail.
Yes, that's true. Yes, another origami style folded up thing that had to deploy in space. One thing I will jump in to say though is that for the deployment and everything having to go just right, and Nathalie mentioned like 300 mechanisms having to operate perfectly. When the Hubble Space Telescope, what kind of thought of as the predecessor to JWST, which launched in 1990, when it launched, and it arrived in its location where it was meant to, which is just in orbit around Earth, where it was meant to start doing its science. It turned out there was a flaw on part of it, and so NASA wound up actually sending a crewed mission on the space shuttle to have astronauts repair the Hubble Space Telescope while it was in orbit. And I like pointing this out because with JWST, it is 1.5 million kilometers away. It is not like Hubble was, a couple hundred kilometers above the Earth. You could go fix it with astronauts, but if there were a problem with JWST, it would just be decades and billions of dollars down the drain. So the precision, the perfection, the amount of testing and retesting that they had to do to make sure that this thing deployed properly and would operate correctly was so important. So I think everybody involved was extremely nervous because, if anything went wrong, there's nothing you can do to save it. Even if we still had a space shuttle that could just bring astronauts up, fairly easily, you wouldn't be able to get them out this far. So it was really quite high stakes. So I'll hand it back over to Nathalie to keep talking about the actual telescope.
It's funny that you mentioned the Hubble because, I was very young when the Hubble sort of was first deployed, and it was a talking point on every late night talk show, and every comedian had a bit about how foggy the Hubble telescope was when it showed up. But you're right. I mean, one of the things I think that a lot of people lose when they don't have the background in space is just the sense of scale. And this thing is way out there. It's very far away in terms of being able to sort of go up and fix this. So actually, I'm going to ask you to drop that video and bring up the schematic of the JWST. We can talk a little bit more about what it does and what the shape of it is. So Nathalie, we have that's a heat shield. Is it on the bottom?
Yeah, so it's a sun shield. That's the part that's about the size of a tennis court. 5 layers of a very reflective material called Kapton. And combined together, it's the equivalent of a sunscreen with an SPF of about 1 million, a factor of 1 million. So it blocks out the great majority of the sun heat, light, radiation, which is very important because Webb is an infrared telescope, very sensitive to heat. If the sun is heating up the telescope itself, the telescope will start radiating in the infrared and cause its own light pollution. So that piece alone required 132 mechanisms for perfect deployment, and it all went well.
That's incredible. Now you mentioned the infrared element of this, and I've talked about it before, this idea of the difference between visible and infrared, but it would be great to hear it from somebody who studies in the field. Is there a quick sort of explanation of why would infrared be any better than seeing in the visible spectrum?
Yeah, so essentially for people who are less familiar with the electromagnetic spectrum, there are all different kinds of light. The type of light we're most familiar with is visible because that's what we can see with our own eyes. But there's a reason why we can see it, that particular type of light. It's because the sun peaks at that kind of light. So through evolution, we've developed eyes that can sort of like profit from the kind of light around us. But different temperatures create different kinds of light. Different objects at different temperatures will glow at different kinds of light. And so you have infrared, but you also have ultraviolet, even radio waves. People don't realize that's a kind of light as well. So for Webb, one of the original decisions to make it an infrared telescope is because we wanted to look at the very first structures ever created in the universe, those very first galaxies, a few 100 million years after the Big Bang. But the funny thing is, they don't actually emit infrared light. They emit very strongly in blue and ultraviolet light. But because of a phenomenon called redshift caused by the expansion of the universe, those very distant objects, the light they emit is stretched out from blue to red and infrared light. So those very first galaxies, by the time the light gets here, appear in the infrared, so they are invisible to a telescope like Hubble. So we needed to build a telescope like Webb in order to see them. But along the way, lots of other things are glowing in the infrared as well. Exoplanets is a great example. And exoplanets have only really been around in terms of a research field for a few decades. Hubble was launched before the first exoplanets were detected, but they were incorporated in the design of Webb. So it's going to do really fantastic things in the infrared for exoplanets.
And to our viewers who might not be familiar, exoplanets are planets that are exterior to our solar system.
Yeah, that's right.
And
there's like a lot of them.
Yeah. And essentially that's where we would hope to find life if life's out there.
Yeah, some people are still searching in the solar system. It's sort of a race. Who will find life first, solar system people or exoplanet people? They have proximity in the solar system, but we have numbers on our side in exoplanets. Lots more candidates. And the Canadian instrument on Webb is actually a fantastic tool to probe the atmospheres of these rocky exoplanets and determine if there's interesting molecules like water or oxygen, things that might indicate that these planets are habitable or maybe even inhabited.
So what is the Canadian element to the Webb?
So it's actually a double instrument. We gave them a 2-for-1 deal, and the first component, it's not a scientific instrument. It's what we call the fine guidance sensor. It's the guiding camera. It's sort of like the eye of the telescope. We have a Canadarm on the space station. We have a Canadi on the space telescope here. And it allows the telescope to find and lock on to celestial targets, despite the fact that the telescope is moving, it's orbiting through space, and it allows the telescope to compensate for that movement. So even though it's not a scientific instrument, it is mission critical, and every single image that you see come out of the telescope was enabled. The resolution and high amount of detail was enabled because of that Canadian eye. So very, very important. And then the second component is a scientific instrument called NIRIS. It's a combination of a camera and a spectrograph, which is a type of instrument which breaks apart light into individual colors. And it'll be able to do research on those first galaxies that were created in the universe and the exoplanet atmospheres we're very interested in.
Well, we'll get to that in a moment. We might as well bring up the first image, the deep field image, and start chatting about that. So Sacramento would be the deep field image on our list of images here on the shareable Zoom In site. And we'll actually discuss these. So this was the first image that was released to the public. I mean, I think it was July 11th, so it's exactly, well, I guess, is it exactly a week ago today? And it was run past U.S. President Biden before it was released to the public. We all saw pictures of how excited he was to look at a picture of space. But it pretty much, I mean, blew up the internet, for lack of a better term. Kate, what were your first thoughts when you saw this image?
Oh, I was extremely excited. Even when I heard that the first one was going to be a deep field, because the deep field images were my favorites from Hubble as well, because it's absolutely mind-boggling. So what you're seeing here, it looks like maybe it's just a bunch of stars, but actually, I think just about every single dot is a galaxy. And so a galaxy is a collection of stars, like billions of stars. So what you're seeing is extremely distant galaxies. This whole field of view is about the size of, if you looked up at the night sky and you took a grain of sand and you put it on the tip of your finger and you held your arm up and looked, the amount of sky that grain of sand is covering is like the same amount of sky that JWST was looking at. And basically, if you were out there where the telescope is, it would just look like there's blackness there. It looks like there's nothing. And Hubble took similar images where it looked sort of in between all the stars that it could see at, just a patch that looked like it had nothing in it. And it just collected light for a really long time, so that even very, very faint light, like just a long exposure time, so even faint light could still get in. And what it sees is that there is a lot of stuff out there in the patch that looks like there's nothing out there. So there's thousands of galaxies in a single frame. And some of these galaxies are unbelievably far away. So if you zoom out a little bit more, see the whole thing. So in the center, there are several galaxies that are really bright and white. So they're sort of brighter, whiter. Yes, right in the center there, those bright white ones are closer. they're about 4.5 billion light years away. So that also means that we're seeing the light that they emitted 4.5 billion years ago. It's taken that long because light travels extremely fast, but at a finite speed. So it takes time to reach us. When you're looking at the starlight, or I mean the light from the sun reaching Earth, that takes about a minute. No, 8 minutes to reach us.
Yeah.
When you're looking at the moon, you're seeing what the moon looked like 1 second ago. Like, yeah, that's the kind of thing that's happening. So
well, and that's what I was asking about, the information transfer back and forth to the web. You know,
yeah.
it's a thing when you're crossing these great distances that
Yeah.
even light, the fastest thing that we have, takes time to travel that distance.
Yeah. So those close ones are 4.5 billion light years away. So we're seeing them 4.5 billion years ago. Some of the most distant ones in this picture are over 13 billion light years away.
Well, this ties into I'm going to pull this question up at the same time because it came up just as you started describing this. And one of the questions online was, what are some of the most distant stars and galaxies we might discover? And I believe some of them are in this picture.
Yeah, well, I'm going to guess that it's going to find more distant ones, because I think they took this one fairly quickly, because also Webb is so much more sensitive than Hubble. I think this image only took like a few hours of collection, if I'm not mistaken. Okay, Natalie's, yeah. She's got the numbers, the real expert. And Hubble would have had to take like weeks of light collection to get something like this. So I think with this telescope, there's going to be opportunities to look extremely far, but these ones are, more than 13 billion light years away. The universe is only 13.7 billion years old. I read that the research teams are expecting to be able to see galaxies that are only, as they were only 100 million years after the Big Bang. So this means that we're looking at the earliest you can really see in the history of the universe, because at a certain point you can't see it anymore, because after the Big Bang things were too hot and dense and obscure. You couldn't actually see anything. So once you start being able to see things, that's about what JWST is going to be looking at. So it's going to teach us about how the earliest galaxies formed. It's going to teach us about, we could look back through time in this, like as the title of this event said, this is a time machine. We're looking back through the history of the universe, and you can sort of trace its evolution over that time. So even looking at this image, some of the very distant galaxies that you can see are a little bit like smudgier, and they have less of a normal, what we would see normal galaxy structure, because they're young. They haven't really had time to form yet, so they're clumpier and more irregular. Another really cool thing that's happening in this image, if you zoom in a little bit towards the center, towards those like central images, so on the right and on the left of those, if you're looking at the star that's got the galaxy that's got the really bright sort of like star shape coming out of it, just down and to the right of that, you'll see these sort of bent, curvy. I'm pointing at my screen like this is going to help. You can see yeah, that's right. So on the right and on the left of those white areas, you can see these bendy lines. And this is galaxies beyond these closer ones, whose light is passing by the closer galaxies on its way to us and being bent by the gravitational pull of those galaxies. And this is called gravitational lensing. It's the light being distorted by gravity. And what you're actually seeing, especially with these two sort of longer, again, I'm pointing at my screen, I can't help it, the two longer sort of curved ones on either side. Yes, that's right, where the cursor is. And on the other side as well, that's actually, each one of those is a single galaxy that we're seeing twice, because it's being curved sort of like there is just a phenomenon of the light being bent in a particular way, where what we're seeing is like a mirror image of each galaxy. So it's a completely mind-boggling thing. It's physics in action. It's something that Einstein predicted way back in the day, and it's just really cool to see it in action. I think if you go up and to the right a little bit, you'll see another galaxy that's really beautifully warped. Yeah, just above. Yeah, you see that.
It's
In the
to me
center.
as a physicist, that was one of the most exciting things to me when those were apparent. And I guess maybe that's a question to put towards Nathalie. Is that how do we know what we're seeing are real images of that light being and not an artifact of the imaging?
So we don't expect any kind of warp like that because we took so much time to do a proper alignment of all the mirror segments. We did proper calibration for all that to make sure that there would be no warping. But I mean, these sort of deformed galaxies caused by gravitational lensing is something that we've seen in other telescopes as well. It's a known phenomenon that we've been able to observe for decades now. Yeah, when you observe these things, it's a challenge. Gravitational lensing is great because we're able to see these galaxies. Not only is the light warped, but it's also magnified. So a lot of these we wouldn't be able to see under normal circumstances, but sort of like the downside of it is that they're warped. So we have to actually use lots of interesting algorithms to basically map out the distribution of the mass, not only luminous mass, but also dark matter mass of the galaxy cluster that's closer to us, about 4.5 billion light years away. And that will tell us, okay, if the galaxy looks warped like this, we expect the mass doing the warping to be distributed like this. So you're not only studying characteristics of those distant galaxies, you're also studying dark matter and characteristics of the cluster in between. So it's just so rich. You're getting so much information from these different components of the image.
Amazing. And I'll ask it. I mean, on behalf of viewers and on behalf of myself, can somebody explain to me what these hexagonal star patterns represent? Why, when we're seeing these like sort of flashed out lens flare looking images of the star that couldn't look more like a classic image of a star. I mean, this thing is straight off of a late 70s, early 80s blacklight carnival ride. What are we looking at here?
So they're actually artifacts that are a signature of Webb's mirror. So the great majority of telescopes and mirrors have their own sort of like little artifact for stars, objects that are very, very bright, point sources that are very bright. Galaxies, their light is more diffuse, it's spread out over a larger area. You don't have that sort of saturation that happens. But because Webb has a very uniquely shaped mirror, hexagons that are sort of like in the shape of a sort of larger hexagon, and because it has 3 struts that supports the secondary mirror, all those different things creates its own signature diffraction spikes on the stars. So something that's really good, and it's a really neat party trick if you go to really nerdy parties, is if you see an image of deep space and you see these sort of like 6 large diffraction spikes with 2 medium ones and then 4 little ones diagonally, you know that that's Webb. If you see instead a diffraction spike, which is 4 big ones like that with sort of like a round halo at the center, you know that's Hubble. So if you learn the diffraction spike pattern associated to different telescopes, you can tell which telescope took the image before anyone tells you.
That is a ultimate nerd party sort of flex, and I am happy to take that on and be its ambassador. Well, you know what? I want to look at the other ones. We've had some great questions coming in as well. Saxon, take us up to full screen, and I've got a question to ask here, which has already been an issue that I think the Webb has had. This one comes from one of our watchers, Vern Scheck, and I know that the Webb has already been hit by at least one piece of space shrapnel. Do we expect, is there a dangerous level here of getting hit by stuff that's going to ruin everything everybody's worked for?
Did you want to take this, Kate?
No, you go ahead. I don't know the answer. So
space policy. I don't know. Maybe there was like a political answer to it. So
I know
it's
Kate loves the billionaire space race. She's voiced that before.
Yeah, I think Kate and I agree on that. From her shaking finger, I think we agree on that point as well. So actually, Webb has been hit more than once, multiple times since its launch by micrometeorites. We expect a frequency of about 1 micrometeorite per month. So the issue is that one hit that happened in late May was had a bigger amplitude, was more impactful than we had predicted. But part of the issue is that we don't really know that well the density of micrometeorites at L2. We have some telescopes that we've sent there before, but this is still an ongoing research field, essentially. So we were able, luckily, because of the construction of the mirror, it has 18 segments that can be moved independently. We have a lot of wiggle room in terms of changing the alignment of different segments to compensate for little damage that's done by micrometeorites. But we expect about one impact per month for the rest of the mission. Whether we got unlucky and the one that hit in May was a sort of like once in 5 years event and we got it right at the start, we'll have to see. So the Marshall Space Center is actually the NASA bureau that's really interested in this. And Webb is sort of like a pioneer because we're going to be sending its successor probably in that same area. So one of the things that it's doing on the side is trying to basically get quantitative information on that micrometeoroid environment in that area so that future missions can be better equipped. So there's still lots of wiggle room. We're not worried at all. The hit that we had before, it's been compensated. The telescope is still working above the expectation that we had before launch. So we're not worried about that. So this is science, right? It's a learning process as we're going along.
Absolutely. Well, Saksham, let's bring up Nathalie's spectrum there, because I want to actually talk a little bit about some of the scientific information we're getting from Webb that aren't just images. So we've got that shot of the spectra coming from the exoplanet. That's it there. No, it turns out there's a giant hummingbird in space. So this came out, and unfortunately, you were unable to deliver it to us on the NASA live stream. And again, the link to watching your delivery of it at the time will be in the show notes below. But can you walk us through what we're looking at here? This is possibly even more exciting than some of the images that we see come from the Webb.
Yeah, definitely. So a lot of people, of course, they are in love with the images. I mean, a lot of people are very visual. It's very striking. Obviously, the images are great. But what a lot of people don't realize is approximately 75% of Webb's observations will be spectroscopic. And that is my specialty. I do a lot of work on spectroscopy because a lot of the science is in those spectra. So basically with a spectrograph, what you do is you take the light of a faraway object and you break it down into individual colors or individual wavelengths. Now, people find that kind of odd for infrared because we don't really think of infrared colors, but it's basically infrared wavelengths at different energies, which you can think of as different colors. So for this specific spectrum, what happened is that we knew this exoplanet existed. We knew that it transits in front of its star, which means that the exoplanet passes in front of the disk of the star. And that is one of the ways that we actually spot that these exoplanets exist, because the light of the star will momentarily reduce. It'll be less bright, and then it'll go back up when the transit or the eclipse has sort of passed. But if there's an atmosphere around that planet, some of that starlight will actually stream through the atmosphere around the planet and will be imprinted by different molecules inside of the atmosphere of that exoplanet. So this is WASP 96b, a hot Jupiter, which means it's basically as big as Jupiter. It's really puffy, but it is super close to its star. It takes 3.5 days to go around. Not a very habitable type of place, but it's a very short year, very, very hot, 500 degrees Celsius there, but a really good starting point for a target. And when we looked at the sort of signature imprint of the atmosphere on the starlight, we saw a very clear detection, a signature of water vapor. And we know that water is essential for life as we know it here on Earth. So it is one of those markers that we look for on exoplanets. And this is using the Canadian instrument near us. We are showing how sensitive the instrument is at picking up these kinds of signatures. And trust me, when I saw the data, I couldn't believe that this was raw data. I thought that they had cleaned up the data because there is so little noise in the spectrum compared to what we usually have to look at.
It's phenomenal. And I'm sorry if I missed this. How far away is WASP 96b?
So it's 1,150 light years away. So
And
relatively
we're getting that
far.
clean of data from something that's over 1,000 light years away.
That's right. And one
That's
of the
phenomenal.
reasons is because it is a larger planet, but we have lots and lots of smaller targets that will be observed by Webb as well. TRAPPIST-1 is a really interesting system. Proxima Centauri b, which is the closest exoplanet, just about 4 light years away from us. So yes, gas giants is super interesting, but we're looking at Earth-like planets as well using Webb.
It's phenomenal. I mean, you know, I think it's easy to get seduced by the images that are coming from Webb, but to look at raw data like this and to see that, you know, this is more than just a telescope. It's an orbiting science lab.
Yeah, absolutely. So the 4 science instruments, there's lots of different modes. So they can take spectra, they can take images, they can use a technique called coronography where they block a central star and they take like a real picture of exoplanets, like not a fake artistic representation, like a real one. They can take pictures of solar systems and formations. So many different things that you can do with the Webb telescope.
Amazing. Well, let's take a look at another one of these images. What you know what? This is a personal favorite of mine just because I don't know. It's just an old science nerd kind of thing. Saxon, can you bring up Stephan's quintet? I remember seeing images of this Hubble images and just being blown away. There's so much going on in this picture. I would love somebody to lead me through it, especially if that picture came up on the screen at any point. There it is. Fantastic. Great work. This one to me, I mean, it couldn't look more like a fake image. Like it just looks to me like somebody when I'm photoshopping like appealing looking space images, you're like, I'll grab a couple galaxies and I'll slap them all together. This looks like space, right? But there we go. We've got our characteristic 6-pointed star that's the James Webb picking it up. What's going on in this image? And there's a lot to zoom in on this one.
I'll give this a whirl, and I think Nathalie will have more details to fill in after I give it a shot. But so this is 5 galaxies in one image. The one on the left-hand side is closer to us. It's about 40 million light years away. Wow, yeah, zooming in on that is really pretty astonishing.
It's phenomenal. The amount of
Yeah.
detail there is just
it's really wild. And yeah, and JWST is achieving detail that we've never seen. We've got images of this galaxy collection before, but nothing this detailed. The other 4 galaxies they're farther away. They're 290 million light years away, and they're gravitationally interacting with each other. And one of the things that I find really cool about galaxies is that it looks like it's some kind of thing, but really it's just a gravitationally bound collection of stars with an enormous amount of empty space in between each star. Just like, Nathalie was saying, the closest star to our solar system is 4 light years away. Like, that's a lot of empty space. Even between the planets in the solar system, there's so much empty space. And so between all these stars, there's all this nothingness. So when galaxies pass through each other, they collide with each other, it's not like 2 objects colliding with each other like you'd think of normally, like 2 cars crashing or something. These are 2 things that are mostly nothingness passing kind of through each other, but gravitationally affecting each other. So and eventually it's going to happen. Earth and the Andromeda galaxy are the next galaxy over, and Earth's galaxy, the Milky Way, are eventually going to collide with each other. But again, it's going to be, like ghosts passing through each other, but just kind of swirling each other around. So what you're seeing here is that kind of swirling dance happening as galaxies like pass through each other, interact with each other, gravitationally affect each other. And it has all kinds of effects, like, it stimulates the creation of new stars. I'm sure it destroys all kinds of things. Maybe there's life on some planet that no longer exists because it collided with another galaxy. There's all kinds of possibilities of what effects can come from this sort of dance of the galaxies. But meanwhile, when you're looking at it, it's also just extraordinarily beautiful. It's got a sort of majesty to it. And then what's more, in the background, again, you just got all these other tiny galaxies, like all those backgrounds. I mean, there's stars back there, but I'm pretty sure, but there's that's just also just a vast number of galaxies. So everything that Webb is imaging, there's so much going on. And what I love about it, I mean, my favorite thing about space is that you can appreciate it on a surface level. You can look at this and think, wow, that's beautiful. And you can learn a little bit about it and say, wow, that's interesting. And then a scientist can look at it and deduce all this incredible stuff about the universe that we live in. Like what Nathalie was saying about in the deep field image, how scientists can look at the distortion and calculate things about, you know, the density of the galaxy that is distorting it. There's so much information in an image like this, and it's accessible on so many different levels. And that's why I've been so excited for this mission to start producing images, because there's so much to dig into.
And if I'm not mistaken here, maybe Nathalie can speak to this. I think, is there images, the remnants of a black hole in this image as well?
Yeah, so some things that I can add here. So this is actually a composite image of two different instruments on Webb. So it's the NIRCam, which is looking at shorter wavelengths of infrared in the near infrared, and MIRI, which is looking at longer wavelengths of infrared in the mid infrared. And so, like I was saying, different types of objects at different temperatures shine at different types of light. And one thing that's really magical about the mid-infrared is that dust and gas is emitting light in the mid-infrared itself. So sort of all of the more orangey color, the red color that you can see throughout the sort of white parts of the galaxies, that is sort of the gas skeleton, I've been calling it, of these galaxies. And between the two galaxies, sort of on the right at the top, you have like this big sort of wave. It's a shock wave front of the gas that's merging of those two galaxies, and you have lots of star formation building into that. And the topmost galaxy, you'll see more orange there, and these two sort of jets coming out of the center. And that is, in fact, a supermassive black hole that is actively feeding on gas and dust at the center of the galaxy. We call it an AGN, an active galactic nucleus. And so we've been able to measure the composition of the dust that it's feeding on. It's sort of like a very, very fine sand. It's like a silicate. We can measure the speed that the gas is being ejected out of these jets as well. And we know that galaxy evolution is very intimately tied with the evolution of its central supermassive black hole. So we're able to actually see what the black hole is doing, which tells us a lot about how the galaxy is evolving as well.
It's phenomenal. I was likening this sort of idea to I recently scuba dived for the first time on a trip, and you know, images that we saw of space before and images that we're seeing now sort of remind me of this concept of scuba diving, where you're looking down at the water from above, and then as soon as you put your goggles on and go into the water, just the clarity of what you're seeing brings so much more into play, and you learn so much more about what's going on down there just because you can happen to see it better. It's phenomenal stuff. And you know, this was so exciting to watch these things being presented. Sachin, let's bring up the cosmic cliffs, this famous image of the cosmic cliffs in the Carina Nebula. And we'll take a look at that as our time is starting to run out here. In the meantime, while that's being brought up, we've got a question coming up in here. We've had a couple of these, and this one is pretty indicative of these questions, which are basically, how close can we look at? What are the closest planets that we're going to see when we have a system that's close with signs of life? I mean, you're putting all your money in exoplanets, Nathalie. Is it possible that Webb will help us find life somewhere within the solar system?
Yeah, absolutely. So there's really fantastic programs to do research in the solar system. An engineering image of Jupiter and a few of its moons actually came out last week, which is really fantastic. You can see the infrared image of Jupiter. So basically anything that is beyond the orbit of James Webb is fair game. So it can't look back towards the sun, at the sun, Venus, Mercury, the Earth, the Moon, because if it were to do that, it would essentially fry its system. The whole thing would be heated up. It would ruin everything. So it has to look out. So it is looking at Mars. It's looking at Uranus, Neptune, but some really interesting programs will be looking at the ice moons around Saturn and Jupiter, so Europa and Enceladus. Really interesting candidates for life because there are liquid oceans under a crust of ice. And you can actually sort of, using a similar technique as with exoplanets, you have these water jets coming out of these volcanoes, and with light shining through these water jets, Webb can actually determine what is inside those liquid oceans. So maybe we'll find some really interesting molecules in those oceans as well.
Very non-mercurial view of our solar system. We've got a question coming in from the YouTube chat, which is, how do we actually go about estimating the sizes of galaxies looking at an image like that?
Did you? Okay, sure.
I also don't know. I can't wait to find out.
So one of the things that you need to do because of the projection effect is you need to sort of figure out how far away these galaxies are. So there are a few different things that you can do when doing that. Redshift is typically what we use because, again, because the universe is expanding, as things are moving away from you, their light is being shifted into the red. So the farther something is, the quicker it's moving away from us, the more redshifted its light is going to be. And so there are certain types of molecules that we expect to be in a galaxy. We expect there to be hydrogen, we expect certain things. So we can look at a spectrum of a galaxy, and we know if it weren't moving at all, we would be able to say, okay, this is what a spectrum of a galaxy at rest looks like. But this guy looks like it's shifted a certain amount, and that certain amount is the redshift. And the redshift can be converted to a distance. And so the distance, you can start sort of piecing together, okay, that's how far it is. If I were to bring it to like a standard distance from us, looking at the composition, the types of stars inside, the age of the galaxy, you sort of build how big of a galaxy that is supposed to be, essentially. So you have to like be a real detective and look at all these sort of indirect characteristics of the galaxies, and that sort of pieces together how big you think the galaxy should be.
All right, Saksham, let's bring up that picture of the Carina Nebula. Kate, do you want to take us through your first impressions of this? This is kind of the I mean, to use the pun, was a star maker of the entire thing. And it's an incredible image. I can only assume it's replaced any one of the many Microsoft generic background desktop images on any one of many devices.
Oh, immediately, yes. Yeah, this is a stunning one. This reminds me of the first kind of Hubble images that I saw that really blew my mind, where you see something like this and you just think, that's actually out there, like that actually exists, something this spectacular and beautiful. And the fact that, yes, it really does exist, that still, it's hard for me to fully comprehend that. But yeah, so this is the edge of a nebula, and a nebula is basically just a huge collection of dust and gas. Sometimes they're formed when a star supernovas. It ejects all this stuff. They're also where new stars form. So this is one, as you punned, it's a star maker. So there are stars forming in this nebula. It's called the Carina Nebula. And we're actually able to see stars forming in it, which is something that previous telescopes have not been able to witness. And again, it's just one of those endlessly zoomable pictures. There's so much detail, and it's stunningly beautiful. And I think, again, it's just the beginning. I mean, they just started taking photos and just started collecting data, and they're already delivering this kind of thing. Beyond that, the scientific details of how exactly a nebula works and how exactly Webb's going to image it, this is another thing that I'm excited to learn and do not yet have a great depth of knowledge on. I'm a planet scientist, or a science person specifically, so all of this more cosmological stuff is just really fascinating to me, but I don't have all the details. So I'll hand it back to Nathalie again for more in-depth information on this.
Well, I've got a question specific to this image, and I'll open it to the panel. I mean, I keep hearing it said that this is dust. This is cosmic dust. Well, what is dust on a size scale? I'm assuming that it's much, much larger than the dust that collects on my antiques at home. What are we talking about in terms of this space dust?
So this is actually pretty similar to the soot that you'll have at the bottom of your barbecue. It's actually quite, or your fireplace, or your arsonist slab, whatever you prefer.
Okay, so yeah, you do know. Yeah.
Yeah, so it's actually quite fine, and lots of different grains in there. Polyaromatic hydrocarbon is a lot of the elements that we see sort of littered through there. But I mean, cosmic dust is an easier way to explain it. And one thing that I always love mentioning about this picture, and Webb really opens up a new window on the universe. I mentioned a little bit the magic of the mid-infrared, where cosmic gas and dust glows in that light. Um, for visible light with Hubble, visible light is actually blocked out by this cosmic gas and dust. So nebulae are beautiful, but actually quite hard to study in the visible. You don't see what's going on behind all that dust and gas. The near infrared is sort of in the sweet spot where it actually can punch through a lot of the cosmic gas and dust. So you're able to sort of lift that veil, and actually a lot of the more yellow stars that you see throughout that the cosmic cliffs are newborn stars that are just at the beginning of their life cycles. And that part of the life cycle has been really mysterious for the longest time because it only lasts a few tens of millions of years, which is like the blink of an eye in cosmic timescales. It's really, really lucky to try to catch them in that moment. But typically, they're still enshrouded in the gas and dust that they're sort of like using to build themselves up.
Right.
But using Webb and near infrared, we can actually look at what's going on in those first few moments of a star's life. And we couldn't do this before.
So when you're saying the yellow stars, is that like sort of that line of 4 of them diagonally in the bottom right? Could we zoom in on that section?
There's that one, but if you just move to the left a little bit more, there's one that's especially it like you can actually see it looks like an opening of a cave with like a yellow flame coming out of it. It's right at the center now. If you zoom in,
right to the just to the right, of
a little bit to right. Yeah. A little bit to the right.
Exactly
right there. Yeah.
Wow.
So that's like an opening into like this sort of
that's amazing
area where this new star is being born.
Speaking of which, our comment section's lighting up with baby star quotes. This is your chance to get a picture with the baby star, I guess. This is that's fantastic. Now, speaking to this concept of color, you know, a lot of people keep posing the question. These are beautiful images, and they're composed of beautiful colors, but these aren't true colors in the sense of the visible spectrum of light. Is that correct?
Yeah, that's right. So some people are like, "Oh, these aren't even real colors. Why are you lying to us?" Well, because if we were to show you the real colors, you wouldn't be able to see anything. So we want you to enjoy the pictures. So because infrared is invisible to the human eye, we basically have to like match up certain infrared colors or infrared energies to colors that are actually perceptible to the human eye. So we sort of do that. And this is something that we've done for other infrared telescopes. We do it for X-ray telescopes. If people are familiar with the Chandra telescope, beautiful images, but it's false color because X-rays are invisible to the human eye.
And it's also a technique that's done with microscopy as well, shifting the color spectrum to pick out more detail. So this is, you know, in terms of like you're saying, people are like, oh, why are you lying to us? Well, this is a fairly common technique that people just aren't familiar with because they haven't worked in these fields.
I'd also add, like, it's, you know, the whole point of this thing is to see stuff that you can't see with your eyes. So, yeah, you know, I think it's not like when you're seeing something like a photoshopped photo of a model or something, and you're like, that's not what he looks like in real life or whatever. You know, it's completely beside the point. We see it in planetary science too. There's a lot of images of planetary surfaces where the colors have been enhanced a little bit to highlight differences that are already there, but that are less noticeable. And they do this for scientific reasons so that you can study the differences better. But it's also to show anybody who wants to just look at it, you know, what's going on. So I think you have to wrap your head around the idea that just because it's not the colors that you would see if you were somehow floating in space right next to this nebula, that doesn't mean it's not real. It's just like a different aspect of reality that you're being granted the ability to see.
Well, it's a case in point. I was looking at an image of Venus, and it's like you have that outer image of Venus where it's just this big white sphere, and then when you're looking at the more detailed cosmological or surface image, it looks like this neon globe. but you can really pick out the differences. I don't want to keep the both of you all night long. People seem to be really enjoying this, and I think the biggest reason is because we've got this incredible panel joining us tonight. We've got one last image. I feel terrible to go through all of them and not speak about the very final one. So, Sakshan, can you bring up the Ring Nebula, the Southern Ring Nebula there? Now, this is what's probably most interesting about this is that we've often seen the two images that have come from this side by side. I'm not sure what we'll see here as we bring it up in the gallery, but maybe we could be led through it again. So this is the Southern Ring Nebula. And can you give us a brief little synopsis about what's exciting about this one? Whoever on the panel wants to go.
I'll do my best again to start us off.
Sure.
So this is a picture of a nebula, and this is, whereas the last one we saw was one that's got stars forming in it, this is one from a star dying. So at the center you're seeing a white dwarf star, and it's burned off all of its outer layers. It's run out of fuel, basically. So like a star like our sun, and actually this star I think would have been like our sun originally, is fusing. It's fusing hydrogen into helium, and that's creating all this heat and light, and it's doing so through gravitational forces. It's so big, it's crushing things into like heavier elements, and it's radiating all this heat, all this energy. Eventually it runs out of the lighter stuff to crush into the heavier stuff. And when that happens, if a star is big enough, it'll explode as a supernova, and if it's smaller like our star, it'll turn into something like this. So this is what we're seeing is, I think, potentially what our star, our sun, will eventually look like once it's burned out all of its fuel. That's the broad strokes, my understanding of it. It's also, again, just like extraordinarily beautiful. There is a second image that's taken in the mid-infrared. So this one is near infrared. So this is closer to what you would see with the naked eye. And then there's a secondary image that is
Sakshan's going to take a look
in
at that one, see if we can pull it up so we can compare the two. But this truly is a beautiful image. As we see it there. Again, to be able to witness the birth of stars and a dying star all in this first, just the first of what will be 10 years, a decade's worth of images that are going to come pouring out of this, and perhaps even more, is so exciting. How long is this mission supposed to run for?
So it was originally designed for at least 5 years, hoping for 10 years. And the limiting factor is the fuel. So it's 1.5 million kilometers from the Earth, orbiting around a point called Lagrange 2 or L2. It's relatively easy to stay there, but it is not a perfectly stable point. So every 3 weeks or so, we need to make a mild correction to the trajectory to make sure it stays around that point. And we had a plan for about 10 years worth of fuel at the start of the mission. But the launch went so fantastically well. Thank you, Arianespace, for doing such a good job. And also for the mid-course corrections afterwards to inject it into its orbit. We ended up saving on fuel. And so we are expecting this mission, at least in terms of fuel, to last at least 20 years. So we've doubled the lifetime of the mission because the launch went so well.
It's exciting to think that potentially some of the students and scientists who will be working on this information haven't even been born yet.
That they'd have to be very precocious.
But
yeah.
Some students who are working, sorry to interrupt.
No, go ahead.
Some of the students who are working with like the science teams, like, there's just such a huge, I would say thousands of people working on the science side of Webb who are going to be using the data, directing, using telescope time. So directing where it should look and collecting data. Some of those students who are on those teams weren't born yet when work on this mission started, because it took 26 years from start to finish. So it's this real generational thing where there are people whose entire career has been working on getting this to this mission to this point, and there are people working on it now who, they were just a twinkle in their parents' eyes, as they say, when this thing was first conceived. And again, there's going to be people who are going to be working on it as students who aren't born yet. So it's really incredible to see the lifespan of a mission like this.
Definitely some of the young kids who are falling in love with astronomy through these images right now might end up using data as researchers later.
Yeah.
Amazing. Saxon's found the two images side by side. Nathalie, can you take us through the differences between these two?
Yeah, so one of the key differences here, you see in the left image, which is in the mid-infrared, two stars at the center. So it's actually a binary system that is at the center of this planetary nebula. And the one star that you see more clearly in the near-infrared image is actually the rightmost of the two stars in the mid-infrared. It's more blue, and that is not the white dwarf. It is not the star that caused the planetary nebula. It's friend, its binary buddy. It's still alive, and it's the red star that's to the left of the mid-infrared image. That is the white dwarf, and it doesn't really show up in the near-infrared image because it is once again enshrouded in its dust that it's sort of blowing off layer by layer. You can see sort of like consecutive layers in the nebula of that envelope of the star being blown off. So eventually, the companion star will die as well, will create a planetary nebula, but it's this sort of hidden red white dwarf that is the one that created it, and you need the mid-infrared image in order to spot it.
Amazing. Well, it's honestly mind-blowing. It's so exciting when anything like this comes along that not only has incredible science, that not only has incredible images that can relate to everybody around the world, but something like this captures the imagination of the entire world. It's truly inspirational, and it's things like this that inspire the next generation of scientists. I don't want to keep you all night. I want to thank you both so much for joining us this evening. I know you're both constantly being hounded by media to do appearances and to share. And I honestly thank you so much. And on behalf of our viewers, thank you for being with us tonight. I'm going to ask you a quick question. We're running your information as we go, but I'm going to combine plugs and question in the same sort of outro. My question typically is, what was your most exciting day of research or of science? But since you've both been on the stream before, and I believe you probably both answered that question before, maybe we can ask specifically with respect to the web, what's been your most exciting thing about these images coming out or about the web in general? And at the same time, I'll ask you to give your plugs if our viewers want to follow you or want to check out your other research or any of the other social media engagements that you're doing. Where can they find you? And we'll start with, since we started with Kate at the very beginning, we'll start with Nathalie at the end.
So I have to say that the most exciting part of this mission up until now has been the release of the first images. The launch was really exciting, but if you're thinking of this sort of as a rover mission, launching the rover from Earth is fun, but people are excited about the landing, and we basically landed with Webb with the release of the first images. And the fact that even though there was a technical glitch, I still got to be involved in the NASA release. I got to see the images early, and I got to be somewhat of an ambassador in Canada to talk about how exciting these images are to so many people. It's been so wonderful. I feel so privileged. I still can't believe that I'm part of this mission. I wake up and I just can't believe I have to pinch myself. So really that was a highlight, and so many more wonderful images and scientific results are going to be coming out that I'll get to share with people on behalf of the team. That'll be exciting as well. And so you can follow me on Twitter at AngryAstroPanda. You can also look at all of our activities with the institute where I work at exoplanets.ca. And yeah, also webtelescope.org. That's the Space Telescope Science Institute website for Webb. Otherwise, the CSA has a great website, Canadian Space Agency, NASA. So much stuff is happening right now with Webb. It's hard to keep track of everything to do, but that Kate mentioned it. It is out in the wider world. It's in pop culture now. Random people on the street know what this telescope is, and that makes me so excited.
That's phenomenal. I mean, your knowledge about the web is phenomenal, and your ability to communicate it is top notch. They've chosen a wonderful ambassador, and your passion for science is inspirational. So thank you so much for joining us and speaking to our viewers tonight. Kate, same to you.
I would say that for me, the best part of this, this recent like flurry of activity with the images being released was actually the day after they were released. Because the day that they were released, me and my whole team at the Planetary Society, we were all in action mode trying to get these images out to the public because we didn't get to see them in advance. So we were seeing them for the first time when NASA did their live stream, sharing them with the public. There was like hundreds of thousands of people watching this live stream, and we were among those people. And as soon as each image was released, we were putting it on the website, we were putting it on social media, we were writing the descriptions, we were making sure everybody got to see it. So I didn't actually get to sit down and look at the images myself, really look at them, like really zoom in on them and think about them until the next day. And that was the best for me because I love, again, like I said at the beginning, I love that my job is to share this stuff with other people. It's such a thrill. It was such a rush that day, and seeing the reaction that people had, but then actually getting to have like a private moment to contemplate what I was seeing and what we had just been so busy sharing. That was really, really the highlight for me. Yeah, and I recommend that everybody who's listening to this live stream go and take some time and look at those images, zoom right in, and if you want to read about them. But even just looking at it and contemplating the beauty and what it means that there's something like this out there in the same universe that we inhabit, I really can't recommend that kind of contemplative activity enough. So yeah, in terms of plugs, my email address is there if anybody ever wants to contact me. I'm also Space Kate H on Twitter. I don't tweet a lot, but you can message me. If you're interested in planetary science, the Planetary Society is a great organization to follow. We are at Explore Planets on Twitter, and we're also at planetary.org. We're going to be covering stuff from the James Webb Space Telescope, particularly with a focus on how it applies to planetary science. So that includes planets within our own system. Like Nathalie mentioned, that there's an initial image of Jupiter that's come out already, very cool. You can see a couple moons. You can see Jupiter's rings. We're looking forward to the research that JWST is going to facilitate in our solar system, and then also with exoplanets around other stars. So if you're interested in those kind of planetary applications, definitely follow us. And yeah, it's going to be a fun 20 years.
Well, thanks again, Kate, for joining us. Your knowledge is phenomenal, and it's always incredible for me to have a conduit to continuously complain about the shape of my Planetary Society membership card and that they should be sent out renewals every year. But no, thank you so much for joining us. And I can't stress enough what a great thing it is that the Planetary Society is doing, and your work there is phenomenal. You write wonderful stories for them. And again, thank you so much for joining us tonight.
It's been my pleasure. Thank you.
All right. Well, thank you so much, viewers, for joining us. If you happen to be just catching the tail end of this, I'm the Great Orbax, and you can follow us for hopefully regular streams again here on the Guelph Physics channel on YouTube. Follow Guelph Physics over on Facebook and Guelph Physics on Instagram as well. And also the end of this week, I'll point out that it's the peak of the Delta Aquarids meteor shower. So get on out there and take a look up and see if you can see some shooting stars this weekend. It's always fun. This has been a phenomenal stream tonight. Thank you, everybody, for watching. And and so put up the comment of always to smash that like button if you enjoyed what you see. We'll see you soon. Thank you so much for joining us. Don't forget to have a science-tastic day. Till next time. Oh, bye.